avant de commencer, je veux juste être désolé parce que je vais en fait finalement me présenter en anglais, parce que je me sens un peu brouillé quand je parle en français, mais je serai quand même heureux de répondre aux questions s'il y en a en français à la fin. Donc oui, je commence. So thanks for listening to me when I'm talking English. I'm going to talk kind of about thermal refuges and kind of where we're at now versus where we've come from and where I think we need to go into the future. So I've done a lot of work over the past 10, 15 years on thermal refuges and rivers. And we know quite a lot, but there's still a lot we need to understand a little bit. So that's kind of the basis of my talk today. But the nice thing about talking at a kind of a river thermal seminar is that I don't have to convince people that water temperature is important, but I've nonetheless got a slide to show you that I think it's something we need to know about. So, you know, we've all seen several presentations earlier that the river temperature is rising globally. And from my point of view, I'm particularly interested in this because some of our iconic freshwater fish species like salmon and trout are becoming more and more thermally threatened. So we get heat stress events, particularly when we get temperatures above 22 degrees, roughly speaking. It depends on the species, but that's kind of where we are, more or less. And because of this, we're already starting to see mass mortality events in salmon populations. So out in eastern Canada, for example, we had a mass mortality event of Atlantic salmon back in 2010. In Europe, we had the 2018 and 2022 heat waves. So we had mortality events for salmon and trout in Scotland, for example, just last year. And so under climate change, there's a real risk of widespread loss, not only of thermal habitat, but also of the fish themselves, right? And we're facing potentially complete extirpation of fish species in some of their native range. And that's, you know, obviously a worry. Having said that, we know our rivers are warming, but at the same time, there is a potential solution. So we have these things called thermal refuges, which I like to think of as kind of oases for fish. So when the temperature in the main stem of a river, somewhere like here, is getting too hot, maybe 22, 23 degrees Celsius, what fish tend to do is they will seek out cool water patches like this tributary here. So this is going to be maybe 3 or 4 degrees cooler than the main stem here. And they will move there and shelter, often for hours, sometimes days, until their body temperature drops and until at such a point when the main stem of the river becomes a little bit cooler, and then they will go back into the main stem. And so thermal refuges, I mean, you can think of them very simply, it's just a place that's colder than the surrounding river water. More recently, there's been a bit more kind of detail in the terminology, so people refer to thermal refuges when they're not being occupied by fish as cool water patches, and that kind of, you know, tallies with what Baptiste was presenting earlier. It becomes a cool water refuge when it's occupied by fish. You should be aware that there's a kind of contrast between what's a refuge and what's often called a refugium or several refugia, which refers more broadly to a sub-catchment or an entire catchment that is cooler than one section. So that's kind of where we are. And you know, this is kind of the physical side of things, right? What thermal refuges look like in terms of, you know, thermal imagery. But it's not an abstract concept, right? They have a real biological relevance. And so I've got 2 pictures here that have been taken by colleagues at the University of New Brunswick, and we can see brook trout and Atlantic salmon forming what we call aggregation. So this is like hundreds of fish moving into a small patch of water because they're otherwise going to be too hot and they're going to suffer from heat stress and potentially die. And I want to point out that this is not normal behaviour for fish like this. They're pretty territorial creatures, most of the salmonids. They don't like being together like this, and it really signifies, in my mind, you know, the problem that they're going to face under climate change. The other thing to remember that this is like a buffet for birds, right? So if you want to have an easy meal, you can just go in and catch fish, super easy. On this basis, you know, we know thermal refuges are therefore important, so it's really important to map their locations, and Baptiste has already started to talk about that, and I'll cover that in a bit more detail. But also to understand what drives them, right? Why do they appear where they do in river systems? And so what I'm going to do over the next few minutes is take you through where we're at and then talk about where I think we should go in terms of the future. So between about 2010 and 2022, I've done a lot of work out in eastern Canada, so Quebec, New Brunswick, mapping thermal refuges with a system that I developed alongside colleagues in Canada. So by a helicopter, we've got a pod here. They call it a helipod. I think it's what people use for heli skiing, but we chopped a big hole in the bottom of it. And we put these 2 cameras in, so we've got a thermal camera and an optical camera. And over about 12 years, we've flown roughly 2,000 kilometres of river in Canada. And the data we've been able to gather from this is quite extraordinary in my mind, because just from a raw data set, we're actually able to identify the locations of all these thermal refuges that we've seen. And this data is already being fed back to some of the river managers we work with, who are prioritising, which ones should be protected. Should we close fishing in this region because there's more thermal refuges than others? And it poses questions, right? This is the density of thermal refuges in the refuge watersheds in eastern Canada. And we can see some rivers, you've got tons of thermal refuges. So if you're a fish there, you're probably going to be fine. We've got other regions where we have very few thermal refuges. And if this river starts to heat up, then you're probably going to have problems if you're a fish. So the raw data is really useful, but I'm actually interested in trying to go a bit further and understand what's driving these patterns. What is causing there to be more thermal refuges here than in other regions? And the first step to doing that is to actually understand where these thermal refuges come from. And this is quite an old paper now that I worked on, and based on some typologies that were developed by Joe Ebersole and Christian Torgerson, who work on the Pacific Northwest in the US. But they basically identified kind of two broad types of thermal refuges, right? Those that are driven by surface water processes, like the channel network, the drainage network, and those that are driven by groundwater processes. And what we see from our thermal imaging data is that the surface-driven thermal refuges are much more temporally stable, and that kind of makes sense, right? Unless you have an intermittent stream, which is quite rare where I'm working here in eastern Canada, most of the thermal refuges will persist the whole summer if they're driven by the channel network. However, what we see is that the groundwater-driven ones, so we've got what we call a lateral seep here, a spring brook, a cold side channel, these are much less temporally stable. And what we see is that depending on seasonal groundwater levels, these thermal refuges can come and they can go. And at the same time, they're actually more abundant than the surface water-driven ones. So if you're a fish and you're searching for thermal refuges, but you arrive at a time of year where the groundwater levels are really suppressed, like now, for example, in the UK, we're undergoing a hydrological drought, these kind of thermal refuges might not exist. And so that's the kind of, the first stage of understanding what drives thermal refuges. But actually, there's been some work I've done out in eastern Canada and some work the Hervé's group has done here in Lyon to really kind of get into detail about what drives their spatial variability, right? So where they are across a watershed. And I think it's quite nice to talk about two distinct scales of thermal refuges. At the kind of riverscape scales, so at large scales, catchment-wide, what we see is that generally speaking, the groundwater-driven refuges are driven by three kind of interlinked processes. So they occur generally more frequently when we have moderate channel confinement, so not really tight valleys, not very open ground, but somewhere a bit moderate where we have kind of offline wetlands, marshland, that favours groundwater upwelling, and so we're kind of more likely to have thermal refuges in this kind of scenario. We often get more thermal refuges at the apex of meander bends, and that's simply because the river is actually kind of meandering out and carving into the groundwater flow field, so we're going to favour groundwater exfiltration in these kind of locations. And then finally, interestingly, a lot of the time if we have dry valleys, we still have thermal refuges at the kind of confluence of the dry valley, because what's happening here is there might not be any surface water flow, but there will still be subsurface hyporheic flow, which when it reaches the river channel will be forced to upwell and will create a cool groundwater patch. So that's kind of the large scale. And then, like I said, Hervé's group has done some really nice work looking at kind of the more, what I would consider kind of reached whole river scale geomorphic processes and how that links to thermal refuges. So Vincent Lazignac, a few years ago, did some work linking thermal refuges to the presence of gravel bars. We've seen recently Theo Bulto's thesis where he attempted to link the presence of thermal refuges to fine sediments and clogging. I think maybe the jury's still out, but I think that's an interesting avenue for research there. And Baptiste just presented some work a few minutes ago where he links the density of thermal refuges to non-flowing channels, right, in braided stream networks. So we know quite a lot. But there's quite a lot we don't know, right? What about differences in thermal refuge densities across regions or across different geological types? And so that's kind of where I'd like to go with the next few minutes of my talk and think about where we need to go next in terms of thermal refuge science. Because in my mind, despite the fact that we've made quite a lot of progress over the last 10 or so years, there are still many, many unknowns about thermal refuges in terms of both their biological significance and in terms of their hydromorphic context. And I'd like to identify 3 areas for future research, which I think we as the kind of the river thermal community need to target. And the first one of those, and I'll talk a bit more about each of these points in detail in a slide's time, but the first one of those is to think more about surface water-driven refuges. Both the work I've done and the work that Hervé's group and Baptiste have done kind of focuses more, in my mind, on the groundwater-driven ones, but I think the surface water ones are just as important, and potentially more so, because as I said, they're more temporally stable. We also need to think more about controls on refuge size and their magnitude, right? How warm or how cold they are, because that's, in my mind, something that we haven't done enough work on. And finally, like I said, I think we need to look more about what drives thermal refuges across different regions. So if we think about that first question, surface water-driven refuges, they are of really high importance to soundwaves, right? Because they are temporally stable. And interestingly, in some areas where I work, like in Scotland, we have very, very impermeable, dense bedrock terrain, so we don't actually have very much groundwater upwelling. So the only thermal refuges that we have in certain parts of the world might be the surface water-driven ones, and yet we haven't really done much research into them. What's interesting, I think, is that potentially surface water-driven thermal refuges present an opportunity for water temperature management. And I'll try and explain what I mean here. So in Scotland, many of most in fact of the rivers are pretty much devoid of tree cover. Right? They're completely open, there are no trees. So intuitively we would think of the headwater as being generally a cool part of the river. But in Scotland often the headwaters are some of the warmest parts of the rivers because the water volumes are very, very low, they receive tons of solar radiation and they warm up really fast. So maybe one of the ways we can manage spring temperatures is actually by creating thermal refuges, by planting woodland in some of these cool tributary headwaters, cooling them down and creating cool confluences which can be used by fisheries. And that's something I'm working on with colleagues at Marine Scotland. I'll be talking a little bit more about that later today in my talk for IS Rivers if you're interested in hearing more about the modelling we've been doing on that front. The other thing I think we need to look at in more detail, like I said, is what I consider the unexplored dimensions of thermal refuges. So the work I've mainly done in the past has just been identifying where thermal refuges are throughout a watershed and classifying them, like just producing simple maps. What I really like is the kind of stuff that Baptiste has been doing, that he showed you a few minutes ago, where he's not only looking at where they are, he's looking also at their temperature dimension and their size, right? And I see this as really interesting because I think it's a way of linking the thermal refuges themselves to actually the temperature, the thermal structure that we see in a river temperature long profile. Because clearly the two are not independent, they're clearly linked, and yet we've never really made the link. So I'm wondering if there's a way of using potentially the size and the distribution and the temperature of thermal refuges to kind of almost come up with a proxy for things like groundwater upwelling and use that when we model these temperature long profiles to better understand if we have these cooling zones like this. And I think one of the ways in which we can do that is coming up with a revised hierarchical classification scheme for thermal refuges that doesn't just say, oh, that's a tributary plume, that's a spring brook, that's a lateral sea, but it also thinks about their size, their temperature, and alternative sources of cool water like karst systems, because where I work, there isn't really a kind of karst system of geology, but in France, obviously, there is. And finally, we need to think more outside the box, right? Most of the work on thermal refuges has been done either by me in Eastern Canada here, been done by Hervé's group, Baptiste, Vincent, etc. in France. But there's actually tons of thermal infrared data across the world. Stuff from the Pacific Northwest, Christian Torsten's group. I've got more data from the UK, there's data from Switzerland, Sweden, Norway. So I think there's great potential for understanding the global scale drivers of thermal refuges. And so that's where I think we should go for the future. That's the end of my talk, and I'll be happy to answer any questions later on.
Thank you very much, Steve.